Hello everybody, and welcome to exercise 1 on page 45 of the workbook. Let's take a minute just to read the instructions on this. So for each of the following linear transformations, they'd like us to find a basis for the range of t, and then also to state the rank and the nullity of t, and then to decide whether t is 1-to-1 and whether it's onto. Okay, so lots of stuff to do here. And in this video, we're going to look at just part B of this. Right, so we'd like to answer all of those questions for the linear transformation that goes from R2 to R3 that's defined like this. Okay, now fortunately we have kind of a nice way of determining what the range of a linear transformation is. Okay, and it comes by kind of looking at the form of our transformation and forming a corresponding matrix. Okay, so we look at the first output coordinate here, x1 minus x2. That would give us a corresponding row in our matrix that looks like 1 and -1. And then x1 plus x2, that would give us a 1 and a 1. We're just kind of reading off the coefficients. And then x1 plus 0x2 would give us a 1 and a 0. Okay, and we've talked about from our previous work how the range of the linear transformation is just the span of the columns of this matrix. We know how to find a basis for a subspace like that. We just do row operations. Okay, and if you do that, you will wind up with a reduced matrix that looks like this. And what it comes down to is to identifying what the pivot columns are here. So let's circle our pivot positions. Notice that we have a pivot position in every column in this case. And that tells us then that both of the columns in the original matrix are pivot columns. Okay, and so our basis is going to be comprised of both of those columns. Okay, so here's the conclusion that we can draw then here. So a basis for the range is going to be both of the columns of our original matrix, since they're both pivot columns. Okay, so there's our basis for R of t. And since there are two vectors in that basis, that means that the rank of t is 2. Okay, well, what about the nullity of t? Well, we can now figure that out just using the dimension theorem. So the dimension theorem tells us that the nullity is going to be the dimension of the domain minus the nullity that we just calculated, which is 2. And that's going to give us 2 minus 2, which is just 0. Okay, so we've got a nullity of t, which is 0. All right, now the last two questions that they asked us are whether this function is 1-to-1 and whether it's onto. Let's tackle the 1-to-1 part of this first. Okay, well, notice that the nullity of t is 0. That means that the null space contains only the 0 vector and tells us that this is 1-to-1. So we can say this. Okay, since the nullity of t equals 0, we see that t is 1-to-1, and maybe just a reminder of the theorem that we used. Okay, that was theorem 2.4 that allowed us to argue that way. Okay, now what about onto? Well, it's awfully tempting after the problems that we've done to say, oh, well, theorem 2.5 says that since t is 1-to-1, it's also onto, but remember, we have to be careful. For theorem 2.5 to work, our domain and our codomain have to have the same dimension, do they? Not in this case. Okay, v is R2 and w is R3. Those do not have the same dimension, which means we can't use theorem 2.5 here. Okay, we have to use a different method. Okay, so what we could do to decide whether this is onto is just to ask, compare the sizes of our codomain, which is R3, and our range. Okay, notice that we have a rank of 2, which tells us that the dimension of the range is 2, but the codomain has a dimension of 3. We know then that it's not possible to hit everything in our codomain. Okay, so here's what we can say then. So since the rank of t, which we just argued was 2, is less than the dimension of the codomain, okay, it follows that T is not onto? Okay, and I think we've answered all the questions they wanted us to.